Hey folks, thanks for joining us. I'm really excited today to talk about taking your AI workloads from research to production using our AI hypercomputer architecture. And I have three of the incredible co-presenters joining me today. I have Maulin Patel. He's the Director of Product Management for GKE. And I also have Curtis Kim, CEO of Kakao Brain. They're building some amazing foundation models for use cases like content generation to healthcare. And I also have Andrew Clare, CTO of Nuro. If you've noticed, if you're around in Bay Area, etc., they have some of the cutest delivery vehicles. They're bringing AI to robotics on the road. So really excited. We have a lot to cover, so let's get started. We are very fortunate to be living in an era of AI. The accuracy of AI models across a whole range of use cases is just amazing, something that was previously thought impossible. And AI models are not just understanding our world, but they're also generating our world today. However, from use cases like content generation to music composition, predicting protein structures to recommending content to customers, etc., you name it. However, that's not really news to this audience. It's all very exciting. But what keeps us up at night is how do we take all these state-of-the-art models and productionize them into our enterprise workflows. And as you do that, there are a lot of challenges. It's incredibly hard. We call that generative AI second act. But there is very complex skill set and software that's needed. There are a whole bunch of tools that open source community as well as various startups and established enterprises have created. However, those tools don't necessarily work well together. And just to create an integrated pipeline that delivers performance and productivity is a big challenge. Once you have the whole pipeline set up, getting access to infrastructure is a big challenge. And if you get access to this expensive infrastructure, keeping it productive, measuring the ROI of your AI initiatives, etc., is an incredible challenge. It turns out that at Google, we've been working on productionizing AI at large scale since our founding by the two researchers in AI over 2 decades ago. There are 5 pillars to our AI engine. First is the industry-defining AI research. Google created Transformer, which quickly became the fundamental building block for large language models. Transformers allowed us to map relationships to sequences of extremely large length. And once we basically take all this research into our state-of-the-art models. Earlier today, we saw in the keynote how our Gemini is powering some of the amazing use cases. However, it's not enough to just have these models. We have to take these models to production deployment. And that's where some of the capabilities that we bring shine, because we have the experience of productionizing AI using some of the largest applications that have over 1 billion users, including Gmail, YouTube, search, ads, maps, etc. And so all the learnings that we have from developing and running these applications at large scale, we contribute back to open source software, including frameworks like TensorFlow, JAX, our compiler XLA, and Kubernetes, with our managed Kubernetes as an example of what you can run today. And finally, to run all of this, you need incredibly performant and scalable infrastructure. So those are the 5 pillars of our AI engine. And we bring our AI engine to our cloud customers via what we call the AI hypercomputer architecture. There are 3 layers to our AI hypercomputer architecture. The base is the performance-optimized, purpose-built infrastructure. It consists of our GPUs, TPUs, CPUs, all interconnected using some of the highest bandwidth interconnects, as well as integration with the storage technologies across the different workflows. That's the base. That's the base. The idea is to deliver exceptional performance and efficiency. And in order to run all of this infrastructure, we have extensive open software. And we'll talk a little bit more about that shortly. And on top is our consumption models. So while we, of course, support the traditional cloud consumption models, including long-term reservations, on-demand consumption, as well as spot, we also have some purpose-built pricing and consumption models just suited for AI workloads, including the dynamic workload scheduler. And our managed AI stack, fully managed AI services, including Vertex AI, sits on top of our AI hypercomputer to support our customers with higher levels of abstraction. Powered by our AI hypercomputer, we're getting some great feedback from analysts. Just last month, Forrester released their wave, where they highlighted how we have strength, not just in our current offerings, but our strategy going forward. In fact, we received highest marks of any vendor in their report on both of those dimensions. And we received full marks in 17 out of the 19 criteria that they had to evaluate different AI infrastructure solutions. And of course, so it's no surprise that our customers are relying on Google Cloud to transform their AI workflows, from technology and innovation industries to financial services, consumer goods, retail, media, entertainment, medicine, and healthcare. We are working, and we are fortunate to be working with a whole host of customers across these industries. And today we'll have two of our pioneering customers share their experience on productionizing AI on Google Cloud. So let's start by looking at the advancements we are bringing at each layer of our stack. And at the base is, of course, our performance-optimized hardware. So before we go deep, let me take you behind the look into our warehouse-scale AI data centers.
To show you how the AI hypercomputer comes to life in a data center, let's think about how we set up a training job for machine learning.
Now, this is where it all begins, with the performance-optimized infrastructure that is at the very core of AI hypercomputer. A scheduler or an orchestrator kicks off a training job that creates a compute cluster. For AI workloads, these instances use accelerators like NVIDIA GPUs or Google Cloud TPUs. This is a compute engine rack filled with A3 VMs powered by NVIDIA's H100 Tensor Core GPUs. Our custom-designed 200 gigabit per second intelligent processing units, or IPUs, create a separate data channel for GPUs to communicate with each other and bypass that CPU host.
A TPU is a tensor processing unit. Each chip has tensor cores with 4 matrix multiplication units, or MXUs, that do the actual arithmetic. TPUs are custom-built in-house. They're specifically designed for artificial intelligence. It's all in there. On a single machine, TPUs can have 1, 4, or 8 chips, and multi-host workloads can use hundreds or even thousands of these chips together as a pod or a pod slice. Multi-slice training jobs can even use tens of thousands of chips. This is all amazing. Everything in here is at a scale that it's just hard to wrap my brain around.
And you know, when we moved to OCS for networking, we created the opportunity to reduce power consumption by up to 40%. This high-performance, energy-efficient, power-dense infrastructure offers a path to more sustainable IT. We hope that you all enjoyed this look into what makes AI hypercomputer a reality.
Wow, isn't that incredible? Every time I look at the scale, complexity, and size of our AI infrastructure and how everything just works, it just blows my mind. Let's start with our cloud TPUs. We created cloud TPUs or TPUs almost a decade ago in order to address the computing demands of our own AI workloads. And today, some of the pioneering services that you're used to, from Gmail to Maps to Search to Ads, YouTube, they're all powered by our cloud TPUs. Our latest Gemini model was trained and is served on our cloud TPUs. We are on the 5th generation of our TPUs, and earlier today, we announced general availability of TPU v5p. TPU v5p is our most powerful, scalable, and flexible cloud TPU to date. For training large language models, TPU V5P provides almost 3x more performance compared to our last generation. And what that means is you can bring down the time it takes to train the largest models from months to weeks. It's also powered by the world's highest bandwidth inter-chip interconnect in production today. Each chip is connected to every other chip, 4,800 gigabit per second of bandwidth, and they scale to 9,000 chips in a pod. And together with the incredible ICI, as well as the scale to 9,000 chips for distributed parallel training applications, we provide 4x more scalability. And finally, powered by 95 gigabits of HBM memory, there's a whole range of AI models that can fit in the memory capacity, from the regular dense decoder large language models to the more advanced mixture of expert models. TPU V5P supports the full range of models for training. We also have a variant of fifth generation of TPU we call V5E. It's designed for cost-efficient performance. It's our most efficient, versatile, and scalable TPU. For training large language models, it provides up to 2.3 times more performance compared to our last generation TPU. And for serving, it provides 2.7 times more performance. It's also incredibly versatile. It supports a whole range of precisions, and it supports shapes from one chip shape all the way to 256 chips interconnected by our inter-chip interconnect. So you can run small models, as well as you can go all the way up to 2 trillion parameter models to run them efficiently for inference. And finally, because it's a TPU, it's designed to scale. Last year, we announced the world's largest scaling training application, scaling a workload to 50,000 chips and delivering great performance. In addition to our cloud TPUs, we also support NVIDIA's cloud GPUs, or NVIDIA's GPU in our cloud platform, and we provide industry-leading capabilities. We work very closely with NVIDIA to optimize the GPU platform on Google Cloud, and there are 3 pillars to this partnership. First, it's the speed to market. We were the first cloud to bring several NVIDIA products, including L4, A100, T4, as well as the P4 GPUs in the past. Earlier at GTC, we announced we're bringing Blackwell to Google Cloud early next year. Second, it's the breadth of offering. We have a full range of GPU accelerators on our cloud to serve small models, mainstream models, as well as gigantic models, and also to train the full range of models. Finally, we are working very closely with NVIDIA to optimize the software stack so you get the best performance, productivity, and usability on top of GPUs within Google Cloud Platform. And we'll talk a lot more about some of those projects shortly. For training the largest models, as well as for serving them, we have A3 based instances, which are powered by NVIDIA's H100 instances. And we announced that the general availability of a variant of A3 called A3 Mega is happening next month. It doubles the bandwidth of accelerators from A3 to A3 Mega, and that bandwidth is 18 times more compared to our A3 instances. Each of the A3 Mega basically can scale up to 26 exaflops of computing. So you can buy instances at a smaller scale of up to 8 chips in an instance, all the way to 26 exaflops of computing in a gigantic supercomputer. And several of our pioneering customers use A3 to power their AI applications today. In addition to A3, we also have L4-based G2 instances. These are designed for very efficient serving of mainstream or smaller AI models. And we are looking forward to bringing NVIDIA's next generation Blackwell GPUs to our cloud early next year. There will be 2 variants. There is B200 and GB200, which uses ARM-based Grace chip, and it's available in the rack scale architecture of 72 GPUs connected by next generation of NVLink technology. Together with NVIDIA, we'll also network these instances using the next generation of NVIDIA networking technology. And because these chips are so powerful, they consume a lot of power, they need to be liquid cooled. This is where we again have a big advantage because we've been working on large scale liquid cooled data centers for a while. We are on our third generation of large scale liquid cooled data centers with our TPUs, and Blackwell GPUs will be featured with our fourth generation of liquid cooled technology at scale. Ultimately, it's the full range and portfolio of products that we offer to our customers, including a full range of GPUs as well as our TPUs, because AI is not just one workload. There is a big difference if you're running a small model for inference versus you're training the next generation frontier models. And no matter what's your workload, from small scale inference to the gigantic training, we have the right instance for you. Let's move on to our second layer, which is our open software enhancements. At the foundation of our open software is our Kubernetes engine. And to talk more about that, I'll invite Maulin Patel, Director of Product Management for GKE.
Thank you, Paresh. Good afternoon, everyone. My name is Maulin. I'm the Director of Product Management in Google Kubernetes Engine. A large number of our customers, such as Anthropic, Cohere, Character AI, Nuro, Walmart, many others, have built their AI platform on Google Kubernetes Engine. We studied their motivation, and we found 3 core reasons why they chose Google Kubernetes Engine. The first one is portability and customizability. Many of our customers are training and serving models across multiple cloud and on-prem. They want the freedom to write their code once and run everywhere. They also want to support many different machine learning frameworks. Kubernetes allows them the portability and customizability. The second key reason is performance and scalability. Many of our customers, such as Anthropic, are training gigantic models with hundreds of billions of parameters. Naturally, they want high-performance, scalable supercomputers to train these models and serve them at scale. The third key reason is cost efficiency. Training and serving generative AI models can be super expensive. Naturally, our customers want lower cost and higher efficiency. They want to reduce the day-2 operations cost. They want lowest possible total cost of operations. So for all these reasons, many of customers have chosen Google Kubernetes Engine as this platform of choice. Google Cloud's state-of-the-art AI platform, known as Vertex AI, also is built on Google Kubernetes Engine. In order to build generative AI applications, you have to address many complex challenges. You have to gather the data, you have to clean the data, you have to extract features, you have to build models, and then you have to provision resources to train these models. Once these models are trained and evaluated, you have to put it in production with live traffic and monitor its performance. You need very powerful platform and rich set of tooling to make this process simple, easy, scalable, repeatable, and auditable. Google Kubernetes Engine gives you the freedom to choose the right tool for your job. I'm super excited to share with you our latest and greatest innovation that will help you accelerate your journey from prototyping to production. The size of the foundation models are growing exponentially. To train massive foundation models with trillions of parameters, you need giant distributed training clusters. These clusters have to be failure resilient and in order for your training to continue making progress. I'm pleased to share that our Google Cloud TPU team ran world's largest distributed training cluster on Google Kubernetes Engine with more than 50,000 TPU v5 chips. That's a remarkable engineering feat in scalability and performance. The fundamental challenge in scaling machine learning jobs is to attain higher goodput. So what is the goodput? The goodput is the fraction of time spent doing productive work over the total elapsed time. Achieving higher goodput at scale is very, very challenging. You may wonder why. The reason is at scale, the overheads, the inefficiencies, and the failure recovery times add up very, very quickly, lowering the goodput. For example, in asynchronous distributed training, even a single node fails in a cluster, all other nodes have to wait until the failed node is either repaired or replaced. Naturally, the probability of a single node failure in a 10,000 node cluster is way, way, way higher than probability of a single node failure in a 10 node cluster. In order to recover from failures, you have to take frequent checkpoints. And loading these massive checkpoints can take really, really long time. Loading data to jumpstart the training can also take a really long time. All of this overhead add up very quickly, lowering your goodput and keeping your expensive GPUs and TPUs idle. Our DeepMind team overcame many of these challenges and achieved a mind-blowing 97% goodput while training Gemini models. Although these Gemini models were not trained on GKE, but the lessons learned are transferable. So now I'm going to share with you a series of innovations that Google Kubernetes is bringing to market to help you attain very high goodput. Not only it will help you attain goodput, but it also gives you better return on your infrastructure investments. So let's walk through those. To achieve higher goodput, you want your containers and your models to load as fast as possible. The challenge here is that in a generative AI world, the size of the containers and the model weights can be humongous. And loading them can take really, really long time, keeping your expensive GPUs and TPUs waiting. To overcome that challenge, Google Kubernetes Engine team has launched an innovative feature which allows you to preload your containers and or your model weights in the secondary boot disk. Using this feature, your workload will start really, really fast. To give you an example, the Vertex AI prediction service, which is built on Google Kubernetes Engine, implemented container preloading using secondary boot disk. And they observe a mind-blowing 29x faster time to load 16 GB containers in a running state. To achieve higher goodput, you also want your data to load as fast as possible. The challenge here is that fetching the data live from Google Cloud Storage or any other object store can be really slow, keeping your expensive GPUs and TPUs waiting and lowering your goodput. To address this challenge, Google Kubernetes Engine team has launched Google Cloud Storage Fuse with node local caching. With Fuse, machine learning practitioners can fetch the data from cloud storage using standard file semantics without having to implement cloud-specific APIs. With Fuse, machine learning practitioners can bring their model from other platforms and run directly on Google Kubernetes Engine without having to modify the source code. Not only it supports portability, but the best part of it is it actually speeds up data loading time using node local caching, so your training can be performed much faster and you save time and money. In our experiments, we found that Google Cloud Storage Fuse with node local caching can speed up training time by 2.2x relative to the streaming data live from GCS. Although Fuse improves the goodput, there is room for further improvement. Using our parallel store, you can get up to 6 times faster read throughput relative to Lustre scratch. Parallel store also allows you to store even larger amount of data compared to GCS views with local SSD. In our experiment, we found that using parallel store, we achieve 3.9x faster training time than fetching the data directly from GCS. One of the other challenges inhibiting achieving good put is inefficiencies in sharing your expensive GPUs and TPUs across multiple teams. To overcome this challenge, Google Kubernetes Engine has launched a job queuing mechanism known as Queue, which is open source and Kubernetes native. With Queue, your teams can efficiently share GPUs and TPUs. Each team gets their fair share of GPUs and TPUs, but they can also burst to reclaim the unused GPUs and TPUs of other teams. That's how you get a higher good put. With Queue, your most important jobs get the highest priority, and lower priority jobs can be preempted. Queue also natively supports popular open source tools, so you can continue using your favorite tool like Ray while benefiting from the Queue. I will now walk you through a series of innovations that Google Kubernetes Engine team has brought to market to help you achieve higher good put. But wait, there is even more. Now I would like to invite back Paresh to walk you through our innovations in frameworks and libraries that will help you achieve good put at a higher layer.
Thank you, Maulin. So we work at every layer of the stack, and that's the point of our AI hypercomputer architecture. And we innovate to solve different challenges that emerge. We are in our infancy in running AI into enterprise applications. And so I'm just going to talk about the top 5 improvements and advancements that we are bringing to our stack and that we've launched either recently or that are available at Next, starting at Next. So all of these things that I'll talk about are available for you to enjoy today. Let's start with JAX. JAX is our high-performance numerical processing framework. It's designed for large-scale machine learning. It's powered by XLA, which is a compiler-driven approach to large-scale distributed parallel computing. And together with JAX and XLA, what you get is a single controller programming model. So you can program a gigantic supercomputer and let the compiler do the distribution of how the jobs need to run at each individual devices. And that's why JAX is gaining a lot of popularity at large-scale machine learning applications. One of the things that we've realized is while compiler is really great, there are some instances where you would need to optimize specific algorithms, like if you want to have the most optimized flash attention implementation. And so we created Project Palace that enables our customers to create their own custom kernels that works in conjunction with XLA and that they can optimize further on top of. Palace, along with a whole range of custom kernels for things like flash attention, splash attention, etc., is already available. We also work very closely together with NVIDIA to optimize JAX and XLA for NVIDIA GPUs. And the chart on the middle, you see very high performance on H100 GPUs, close to the best, most optimized performance that you can get on NVIDIA GPUs today with JAX. In order to bring all of these different technologies I was talking about in an easy-to-use, directly consumable form, we created MaxText. It's an open repository with a reference implementation for dense LLMs. You can directly use MaxText for out-of-the-box performance, but you can also customize it further to fine-tune it even more. Now, with all the 5 things I'll talk about, there is a session later at Next where you can learn more about what's happening with MaxText and JAX. And MaxText is available on GitHub for you to enjoy today. Let's build together. The second project I want to highlight is Jetstream. Inference is where AI gets to work. And LLM inference has been a very dynamic field in the recent months. In fact, every day we hear a new advancement that's coming from continuous batching to quantization improvements to ragged attention and so on and so forth. And in the past, we've had many different projects that our customers would have to integrate themselves and deploy. But now we've streamlined everything and combined all of this into a project we call Jetstream. It's designed for large-scale model inference. It's a throughput and memory-optimized inference engine for LLMs, and it supports models from both JAX and PyTorch. And several of the serving optimizations I was talking about earlier, including continuous batching, weight quantization, KV cache quantization, etc., are available already on Jetstream. And it already supports some open models, including Llama 2, as well as our open model from Google, Gemma. There is a session, if you want to learn more, later at Next. And of course, Jetstream is available on GitHub. Let's build it together. The third project I want to highlight is Max Diffusion. The diffusion models are basically used to generate images given the text prompt. And in order to enable our customers to get benefit from all the innovation that's happening to train and serve diffusion models with high performance and productivity, we've created Max Diffusion project. It's a reference implementation, just like how we had NextText as a reference implementation for LLMs. And it brings optimized performance on top of our TPUs, starting with TPUs, with GPUs coming soon. And it's really designed to scale. It provides incredible performance. While latest models like SDXL 2.0 or Stable Diffusion XL, they basically, you get one inference per second or one image generated per second using some of the latest stack. On TPU V5e, using our Max Diffusion, you can generate 6 images every second. So performance is outstanding. There's a session later at Next where you can learn more about this project. And Max Diffusion is available for you to enjoy today on GitHub. Fourth project I want to highlight is PyTorch XLA. PyTorch is the most popular framework that our customers are using to create their generative AI models and to serve them. And in order to bring the benefit of XLA compilers to our PyTorch users, we created PyTorch XLA project. And we've been continuing to advance this project at a very rapid pace. When you run PyTorch with XLA, you get both high performance and portable performance across different XLA devices. Two of my favorite enhancements that are coming on top of PyTorch XLA is, first is auto sharding. Sharding is where you're distributing a large model for parallel processing across the large cluster. With auto sharding feature, the compiler automatically does this distribution. So you just specify the number of devices, and the compiler does the automatic distribution and runs it at pretty good efficiency, very close to what you get while you figure out the right sharding strategies by manual trial and error. The second is the custom kernels I talked about earlier using Palace. You can now use those custom kernels within your PyTorch workflows using PyTorch XLA. This release I talked about, PyTorch XLA 2.3 is in RC, and it's going to be available broadly to our customers soon. Again, there's a talk for knowing more about the work we are doing here, and the project is available on GitHub for you to enjoy. The final thing I want to talk about is the collaboration we're doing with Hugging Face. Earlier this year, we announced that we are doing a big partnership with Hugging Face to bring Hugging Face users to have great experience on top of Google Cloud, and that partnership is already starting to bear fruit. You can run now models from Hugging Face with Vertex AI workflows as well as using GKE. In addition, you can also train and serve models from Hugging Face, not just on GPUs, but also on TPUs. There is a session where you can learn more about the collaboration we're doing with Hugging Face. It's being co-presented by Hugging Face team along with Google. And of course, you can try some of the improvements. They are available on GitHub. The final thing I want to talk about is the consumption model. So one of the big challenges with AI workflows is you can either, in order to get capacity, you can use reserved instances, but you have to reserve them for a really long time, like 1 year or 3 years. What if you have short-term workloads? For short-term workloads, you can use on-demand in the spot, but the challenge is with all the capacity shortages, it's very hard to get instances available in on-demand in the short order. Or for spot instances, your job can get preempted. So to solve that problem, we created dynamic workload scheduler. It's really helpful for a bunch of scenarios. So if you have predictable workloads, like you want to fine-tune your models every month on a couple of days of computing, for example, so you know that, hey, 4 days a month, you're going to fine-tune your models, you can pre-reserve the capacity at a predictable schedule using our calendar mode, and that capacity would be guaranteed to you. You don't have to do long-term reservation in order to just use the capacity for 4 days or a week in a month. The second usage is where your researchers are doing experimentation in order to find the right hyperparameters or adaptability to use cases. Sometimes those experimentation do not have to be time sensitive. And so you would want to queue them up and let the system decide when that experimentation can execute, so you can optimize on cost. You can traditionally run them on Spot, but Spot instances get preempted. With the dynamic workload scheduler flex start mode, your workloads will start at a different time, but they are guaranteed to complete. So there are a whole lot of advancements we went through very, very quickly. But in order to help you understand how our customers are deploying and benefiting from all the advancement we are bringing, let me invite Curtis Kim, CEO of Kakao Brain.
Thank you, Paresh, for welcoming, and it's great to see you, everyone. Let me say it is an exciting time to be in the AI industry, but it's also intimidating moment as well. People in this room probably understand what I mean by that. So here is the foundational model from our company. As a CEO of Kakao Brain, a specialized AI research and development subsidiary of Kakao, I am excited and proud to introduce our cutting-edge foundational models. CoGPT is our 66 billion parameters model, Korean native large-scale language model that outperforms GPT-4 in several Korean benchmarks. Second, Kalo is our image generation model that outperforms SDXL and specializes in portrait photography. And the last, Kharya, is our state-of-the-art medical multimodal model that can produce medical reports in seconds. So, developing these foundational models, we challenged lots of key challenges. But what I mean by intimidating is that we are still in the very early stage of the technological revolution. So there are a lot of technological challenges we need to address. It's a really expensive technology. So a small decision I made can lead to multi-million-dollar cost. In this kind of uncertain market situation, I believe productivity is the key thing. How efficiently are we doing data processing? Are we handling the hardware efficiently? What is the most cost and time-effective way to serving our model? And thanks to GCP, we think we are tackling those issues as pretty well. So as a customer of Google Cloud, let me say GCP is a full-stack AI hypercomputer architecture with productivity its core. We deployed Dataproc for data processing, and we doubled productivity in this stage. For model training, we tested TPU with JAX framework, and we got early outcome promises at least 50% of training cost cut. And JAX and its dev community is evolving very fast, so it's a crucial decision point to reduce the trial and error. And for the inference, we use various mix of GCP platform to fast release our language model for internal usage. It's incredible because it just takes few hours to make a production level API for a language model. So this kind of productivity boost is the exact thing we want to bring into the market. So let me take an example. Kharya, our report generation model, is a good example for that. So here's the demo for Kharya. Kharya is trained on over 16 million chest X-ray images and reading texts. That is the world's largest data set such of in this category. Kharya can produce what we can call first draft of readings in mere seconds, as you can see on the screen. This is a real demonstration. You upload a medical image. The model generates the professional level reports in seconds, as you can see. But it's not just about the speed. Both of our internal validation and independent research indicate that our model already exceeds human benchmarks, and in major aspects, and it's far superior than GPT-4, supercharging productivity of radiologists. As I said, it is exciting and intimidating time to be in the AI industry. With Google Cloud Platform, our models achieve a remarkable productivity boost while maintaining SOTA or cutting-edge performance like this. CodeGPT achieves compatible or compelling results compared to GPT-4 in the Korean knowledge benchmark, but we reduce training costs at half. Kakao, we beat SDXL, but its inference cost will be 6 times efficiently. Kharya CXR, we didn't use the GCP at this moment, but we expect that model training and data processing efficiency will be double. Thank you for the listening, and I'm handling over to the CTO of Nuro, Andrew Clare.
All right, good afternoon, everybody. My name is Andrew Clare. I'm the CTO of Nuro. And I'll kick things off today just by introducing Nuro a little bit to everybody here. Nuro is an 8-year-old company based in Mountain View, California. We've raised about $2 billion in capital from a number of incredible investors, including SoftBank, Baillie Gifford, Fidelity, T. Rowe Price, Greylock Capital. We have a number of partners around the country that we've worked with to deploy our autonomous vehicles into a number of services that benefit communities around the country. Those partners include Kroger, Domino's, Uber Eats, FedEx, Walmart, etc. We build what we call the Nuro Driver. That is our core product. It is an AI-first L4 autonomous vehicle technology product. And I'll speak a little bit later about how we've been partnered with Google Cloud for many years in order to deploy our AI-first technology out into the world. One of the things that I'm most proud about is our proven on-road safety record. We have had driverless vehicles with nobody inside of the vehicle driving since 2020 on roads in 3 different states around the country with a pristine safety record. And we're very proud of that as a company. And what we really have done here is deploy our technology across a wide variety of vehicles, as you can see here on the screen, ranging from custom delivery vehicles on the left that we've built in-house, 3 generations of custom delivery vehicles, consumer passenger vehicles that we use for both testing as well as delivery operations, as well as a Class 8 truck that we've also been doing highway operations with. And we've designed our technology to be able to scale, and I'll speak more about that on the next slide. The Nuro Driver consists of both a hardware suite, all of the sensors, both LiDAR, camera, and radar on our vehicle, as well as an AI-first software suite that allows us to safely navigate the road on both neighborhood roads, commercial roads, and as I said, for Class 8 trucks as well in the future. We have a continuous learning operation which leverages connectivity for a number of different reasons. First of all, to be able to leverage data from on our vehicles for actually taking that data to continuously improve our AI models. Secondly, to deploy over-the-air updates to our vehicles, where we can update anything on the vehicle over the air. And third, of course, as we're deploying L4 autonomous vehicle technology, is when that vehicle needs some level of assistance, it can phone home for help and get some human assistance in those rare cases. One of the things that we're most excited about is that we recently developed and deployed a state-of-the-art transformer-based behavior world model that we used hundreds of millions of driving examples in order to train this foundation model. This foundation model then gets fine-tuned to be able to deploy our in-house planning and prediction models that are leveraging, again, state-of-the-art AI technology. We leverage petabytes of data from the sensors that are gathered on our in-house R&D fleet. As you can imagine, autonomous vehicle technology is very data hungry, very data heavy. And again, this is part of our partnership with Google Cloud to be able to leverage that much data to effectively train our models, but also to run simulation. I'll speak more about that in the next slide. One of the things that we're most excited about in terms of our partnership with Google Cloud is the ability not just to manage all of that data, but to then leverage all of the variety of Google Cloud product offerings to be able to effectively use it. So let's go into some examples. You heard earlier from Paresh about the AI Hypercomputer of Google Cloud, performance-optimized hardware, open software, and flexible consumption, all of which we utilize at Nuro to train the AI-first Nuro driver. Let me give you 3 specific examples. We run all of our cloud compute and GKE clusters with an in-house orchestration that leverages Google PubSub in order to be able to do that in a very cost-efficient and effective manner. The second key example is that recently we started to get access to TPU v5, and we moved all of our ML training from GPUs on TensorFlow over to JAX on TPU v5. We saw with that behavioral world model that I mentioned earlier a 2x increase in ML model training time with no incremental increase in cost, which is a massive speed up in our ability to train really powerful large models such as that behavioral world model. Finally, as I mentioned, we manage petabytes of data. And we recently in-house were developing a lot of different technology for fine-grained application of storage layers and storage access to be able to manage our costs. Yet when GCP came out with GCS Auto Class, it was a game changer for us in terms of our ability to really manage the data access levels that we need in a fine-grained way to achieve really great capital efficiency. With that, I'll hand it back to Paresh.
Thank you, Andrew. You just heard from Andrew and Kim firsthand how they're using Google Cloud to power their AI workflows. AI and creating an AI platform is a full stack problem. And this is our superpower at Google. This is where we shine. We are innovating across every layer of our stack so you can productionize workloads, take them from research to production. We're out of time, but we'll be happy to take questions on the side if you have any. Thank you. Thank you for joining.